Okay, there we go. Okay, record. All right, so where do we, what chapter do we find the most difficult? 13, 14, 13, okay. So is there a question we want to start with in the packet? 12? Okay. You're the loudest. So question 12. Okay. So question 12 is a chapter 13 question. It talks about vapor pressures of a mixture. So in Chem 1210, we talked about mostly pure substances for the majority of the course. You know, when we think about like IMFs present in pure water, IMFs present in pure ethanol. But in this class, especially chapter 13, we talk about mixtures. Yes, we talk about mixtures. So the idea is we're combining different pure substances, making mixtures. We're not breaking or making any chemical bonds, but instead we are breaking and forming new IMFs between the solute and the solvent. So there's a ton of different properties we've discussed in chapter 13, including enthalpy of mixing, and then another one here, the colligative properties for mixtures. So the different colligative properties for mixtures, it's typically, you know, these are properties we measure of the solvent. Okay, you think of, we have pure solvent, it has properties. Let's say water. Pure water has a melting or freezing point of what? 0 degrees Celsius. So once we start adding junk to it, the properties are going to change. And so this is dictated by colligative properties. How much junk you add to your mixture, how much you change the mole fraction of water present, changes the properties that we measure of water. Not drastically, but you see small changes relative to that pure solvent. So the different types of colligative properties that we discussed, the first one being vapor pressure lowering. The more junk, the more solute you add to a mixture, the mole fraction of your solvent. So if you have pure solvent, what is the mole fraction of solvent present? Let's say water. What's the mole fraction of pure water? 1, yes, because all of it is just pure water. But once you start adding stuff to it, let's say NaCl or whatever, you start to see the mole fraction go down. All right, the total moles of your solution of your solvent go down. So one of the first properties that we discussed is vapor pressure lowering. The more junk you add, the more the solvent mole fraction goes down. We see a vapor pressure lowering. Vapor pressure lowering, what else did we learn about? Freezing point depression, all right? So we make sure when we calculate freezing point depression that we subtract that value that we calculate from IMK from the original freezing point, so it always goes down for mixtures. We learned about boiling point elevation, all right? So same principle, more junk you add, the higher your boiling point goes. And what's the last one? What's the last one? Osmotic pressure, yeah, so osmotic pressure is the last one. Higher concentration of stuff in your mixture, higher osmotic pressure that you'll measure. So this question is relating to the first one I mentioned, vapor pressure lowering of mixtures. So in this one, we have at this temperature, we have, I tell you the vapor pressures of pure water and pure ethanol. A solution is made by mixing 125 grams of water and 85 grams of ethanol. So the first part of this question is, what is the total vapor pressure of this solution? So I'm just going to quickly draw what this looks like because that can be helpful. All right, we have a mixture. Most of it is water, right? 125 grams. And then another part of it is ethanol, 85 grams. All right, so we got a mixture. Great. Water, pure water exerts a vapor pressure at this temperature. Ethanol exerts a vapor pressure at this temperature. We know because ethanol typically smells like something. So ethanol is quite volatile. It has a high vapor pressure at room temperature, and we can see here ethanol has a higher vapor pressure in its pure form. So when we have a mixture, we don't have, we're not measuring the pure vapor pressure of any one component, but a mixture of both of them. And so I like, when I teach this, I like to think of it like a weighted average. all right? Each of those components are going to contribute vapor pressure, but not the full vapor pressure. We're not just going to add up 175 and 400. We're not going to do that, all right? We have to take into account the mole fraction present in the entire solution. So the equations that I want to use here is the vapor pressure total above the solution. And what I mean is if we measured, you know, the gas phase above the solution, this is what we are measuring right now, or calculating. The total pressure of this solution is the partial pressure exerted by our water component and the partial pressure exerted by our ethanol. Both of the components. But the problem is, and you know, it's easy to do, you might think, oh, just add these two up. But again, that's the pure form. So to get this, you know, a little bit more specific, each of these components, we have to calculate using the mole fraction of that component and the the vapor pressure in the pure form of that component as well. So each of them have this mole fraction times pure vapor pressure term, but for the respective components. So that means we need to calculate mole fraction for each of those. So let's do that. We're given gram amounts of each, so we need to convert that to moles. So we have 125 grams of H2O. Oh, I even give you molar masses. I'm so nice. We typically do that in 1220 because you don't have time to calculate molar masses. You got to use your brain power. So we usually give you molar masses. And so there's the mole amount of water, and then we have this many grams of ethanol. Use the molar mass of ethanol, so 46.07 grams, 1 mole of ethanol. And so I get that present in this solution, there is 6.937 moles of H2O and 1.845 moles of ethanol. Oh, no. Okay, moles of ethanol, great. All right, so to get to our mole fraction, it's probably best for us to calculate, okay, what are the total amount of moles of solute and solvent in this mixture? So you just add those two up, and you get that the total amount of moles present is 8.782 moles. This is all describing what is in solution, what is in the liquid phase down here. All right, so we're calculating the liquid phase of the mole fractions. So to get mole fractions, we just take the mole amounts of each component and divide by the total. So for water, to calculate this, it's going to be 6.937 over that total 8.782, and we get the mole fraction of water is 0.7899. All right, so this solution is mostly water. We can tell because it's present in a bigger amount. All right, and then we can get the mole fraction of ethanol. It's just going to be the rest of it, okay? Mathematically, it's going to be, you know, the excess to get to 1, a mole fraction of 1, but still mathematically, you know, if you divide 1.8 by that 8.7, you get the mole fraction of ethanol 0.2102. All right, so that's of ethanol. Okay. Now that we have our mole fractions, we can plug it into our Raoult's law. So to do that, I'm going to just copy this little part down here, all right? And I'm going to expand it where the total pressure of this system is the mole fraction of water times the pure vapor pressure of water, plus the mole fraction of ethanol times the pure vapor pressure of ethanol. So now we have all the pieces we need, and it's just plug and chug. I like to think of it, showing it to you this way, it's like doing a weighted average from 1210. Do you remember doing weighted averages when we looked at isotopic masses, natural abundances? Yeah, so like natural abundance is kind of like mole fraction in a way. All right, so we're just taking into account how much of each component is present. So the numbers we put in here, 0.7899. What's the pure vapor pressure of 175? Torr. Plus the mole fraction of ethanol, so 0.2102, times it in its pure form, so 400 torr. All right, and then that'll give us our total vapor pressure above the solution. And so I'm gonna do it in parts here, okay? So given the mole fraction of water, we multiply by its pure form. Water is contributing 138 torr to the total vapor pressure. That's how much water is contributing. Ethanol, on the other hand, is contributing a different amount. It's contributing 84.0 torr. All right, and so the total vapor pressure that we'll measure will just be a sum of those. All right, and so P total here will be, I think 222, maybe, yeah, torr. Okay, that's the total pressure that we measure above the solution in this little picture that I have up here. All right, so one of the questions here is, does the unit of pressure matter, or do they just have to match? They just have to match. Yes, so in this example, it's torr, but if I gave you vapor pressure in ATM, they just need a match. Yeah, great. Okay, so let's think about it. Does this total pressure make sense? Does it make sense given each of the components? Water has a pure vapor pressure of 175, ethanol 400. The vapor pressure of this mixture is between the two. So that makes sense. If you got a vapor pressure of 800 torr, I hope that you'll think about that and be like 800, that means the mixture is exerting a much higher vapor pressure than any of the two pure forms. So that's what I want you to think about. Or if you got a vapor pressure of like 5, that, you know, the total pressure above your mixture is way, way, way lower than any of your two mixtures. Again, thinking about it like a weighted average will help you there. So we just answered A. We used the mole fraction of the components in the solution in the liquid phase, applied it to the pure vapor pressures, Raoult's law, you know, and got that. All right, so B is automatically harder, but having A already finished helps us. So B is, what is the mole fraction of ethanol in the vapor phase above the solution? So let me go back to my little picture, okay? We actually measure this, and it's 220 torr. If we used some type of gas gauge, pressure gauge, it's just gonna spit out 220. It's not discriminating whether it's ethanol or water. It's just, okay, there's 220 torr worth of gas. So this question is asking, okay, how much of that gas is ethanol in a mole fraction? I know the total is 222 torr. So a common mistake students are thinking with this question, they see mole fraction of ethanol and they go, oh, we already calculated that. That's right here. That's right there, right? 21% is ethanol. But what's the problem? That ethanol, 21%, is in where? The solution, not the vapor phase. That's the difference. Very good, very good. So to answer this question properly, I need to bring back a topic from 1210. Dalton's law of partial pressures, all right? Remember with Dalton's law of partial pressures, so if I tell you, what's the atmosphere on Earth? 1 what? Okay, 1 atm. Okay. If I tell you that oxygen is 21% of the Earth's atmosphere, is oxygen 1 atm? Is the partial pressure of oxygen 1 atm? No, it's the total gases, right? So our air has nitrogen, oxygen, a bunch of other crap in it. So oxygen, its partial pressure is actually only 0.21 atm, because when you factor in that percentage. So we want to do the same thing here. So the actual equation for Dalton's law of partial pressure is that the partial pressure of your gas that you're studying is equal to the mole fraction of your gas in the mixture times the total pressure of all the gases present in your mixture, right? We already calculated P total, right? So let me just change this. So we are trying to calculate partial pressure, or sorry, mole fraction of ethanol, and again of the vapor phase. So if we go back and think, okay, what terms do we already have? We're trying to calculate mole fraction of ethanol in the vapor phase. Okay, in the vapor phase, we actually already have P total, right? It's 222. What's the vapor pressure of ethanol? Did we already calculate that too? Look back at when we calculated total pressure of the system. How much of the pressure came from water? How much of the pressure came from ethanol? In this case, it's 84 torr. So to calculate this, we're just going to put in those numbers. 84 torr is equal to the mole fraction of ethanol of the vapor phase times the total pressure of the vapor above our mixture. So what is that, 220 torr, right? And then you solve that, and what do we get? That the mole fraction of ethanol in the vapor phase, is 0.378. So here we got a different mole fraction, all right? So these mole fractions are different. This mole fraction is ethanol in the vapor phase versus, and we went about it using Dalton's law of partial pressures after calculating the total pressure. We also calculated mole fraction of ethanol in the liquid, in the solution, and that just came from the gram mole amounts that we were given, all right? So this is a two-step process. That kind of question on the exam, rather not easy, but easier, but we could automatically make it harder by, instead of asking A, we ask you question B, because you have to do A anyway to get to B. Good, right, so mole fraction of stuff in the liquid solution, mole fraction of stuff in the vapor phase. You got that separated? It's commonly misunderstood. You just see an X and you think it's just mole fraction of whatever, but we gotta be cognizant, is it the liquid or vapor phase? Okay, the questions here, pressure, vapor pressure above solution. So the question is, what is the difference between vapor pressure above solution versus in solution? So vapor pressure above solution is specific for volatile liquids, and so that's like this example. We don't measure a vapor pressure inside a solution. Instead, we measure solubility of gases in a solution. So that's another topic that, yeah, we talked about in chapter 13, the solubility of gases in water, for example. Why, you know, my LaCroix here, why it's carbonated and, you know, pops when I open it because there's dissolved CO2 in here, but the more I talk and the less I drink it, that CO2 goes where? In the atmosphere, away, and then it tastes disgusting. So I need to drink it. All right. So now the question is, I'm wondering how high concentration of solute lowers vapor pressure. That's a great question. So in this example, so that relates to this example. This example, both things have vapor pressures. Both things are volatile. Both things contribute to the total vapor pressure. If we just had salt water, NaCl, aqueous, what are the components in NaCl aqueous? What is NaCl aqueous called? What's the street name for that? Salt water. So what is it composed of? Salt and water. So water has a vapor pressure, right? If this was 63 degrees, it has a vapor pressure in its pure form, 175 millimeters of mercury, torr, whatever. All right. Does NaCl, does a solid salt exert a vapor pressure? No, solids do not exert vapor pressure. So we can still use Raoult's law to calculate the vapor pressure of of a mixture with an electrolyte like this, or non-volatile solute, like sugar, salt, those examples. So I told you before, if we had pure water, all right, if we had pure water, the mole fraction of water is what? What is it? 1. Yeah, so if we plug that into Raoult's law, vapor pressure of your component equals mole fraction of your component times the vapor pressure of that component in the pure form, so that's what that little knot is. What do you get? What is the vapor pressure of pure water? It's 175, because X, or our mole fraction here, is 1. But once you start adding salt, what happens to your mole fraction? It goes down. So what happens to the vapor pressure of water above the solution? It also goes down. So that's why it's called vapor pressure lowering. Okay. You can't hear me? Is vapor pressure and partial pressure the same? It depends. Vapor pressure, I mean, I could mean total vapor pressure. Partial pressure is specific to if I'm trying to designate, oh, there's a difference between the pressure this component is exerting and this component is exerting, I will say partial pressure. But yeah, vapor pressure, the same thing. Yeah. Okay. All right. So there was another question of 5, number 5. Oh yeah, I like 5. Okay. All right, so let's look at some beakers. So we have two beakers, both contain NaCl and water. What's the street name of that? Salt water, yeah. And I tell you, the solubility of NaCl at this temperature is 35 grams of NaCl in 100 grams of water. So what does that mean? That solubility means at this temperature, let's say it's just room temperature. If I have a beaker of 100 grams of water, how much salt, what's the maximum amount of salt that I can add to that solution? And it will go in and dissolve. 35, great. All right, so I can put 35 grams of NaCl can fit in there and completely dissolve. It'll be a colorless solution, a true solution. What happens when I add the 36th gram of salts? Where will it go? It's going to fall to the bottom because the solution cannot hold anymore. What if I add another gram of solid? It's still going to sink to the bottom. There's nothing you can do, once we're at the saturation point other than change temperature to get more stuff to dissolve. We can't just shake it up to make it go in. So this question says, okay, consider these two beakers. One beaker contains 30 grams of salt. The other one contains 50 grams of salt. So let's just think about that. Given the information, beaker A1 is what kind of solution? Unsaturated. The definition for unsaturated is can accept more solid. Because the question, I think that's what A is. Which beaker will accept more solid? Can beaker 1 accept more solid? Yes. We can add 5 more grams, right, until we reach its solubility. So beaker 1. Beaker 2 contains 50 grams of NaCl and 100 grams of water. What kind of solution is this? Saturated. So let's draw the picture. So starting with 100 grams of water, how much will actually go into solution if we put 50 grams in? Only 35 grams of NaCl will actually dissolve. Where does the rest of the salt go? To the bottom. So how much is in the bottom? How much is in the bottom of our beaker? 15 grams. Okay, great. And so B, I guess the answer here is 2. All right, calculate the concentration of NaCl in each beaker in molality. Oh, that's a new one. Okay. So we want to think, okay, what is dissolved? When we consider molality, we want to think about what is dissolved in solution. So I always like to think, what is the unit of molality? Moles per kilograms of solvent. And let's be super specific, moles of what? Solute, in this case, NaCl. Very good. So each of these beakers will actually have different concentrations because we want to think, okay, how much is actually dissolved? So let's look in beaker 1. For beaker 1, how many grams of solid is actually dissolved in the solution? 30 grams. So we want to do 30 grams of NaCl. We want to convert that to moles. So 58.44 grams, 1 mole. That equals something like 0.513 moles of NaCl. And then we divide by kilograms of solvent. Do we know how many kilograms of solvent we have? 0.1, yeah, because it's 100 grams. We started with 100 grams, so 0.1, there's your molality for that one, for beaker 1. For beaker 2, is it any different? Is it any different? Is the calculation different? It's the same process, but we have a different amount of salt dissolved. It's 35 grams. You told me that, only 35 grams goes in. So 35 grams of NaCl, convert that to whatever. You get that beaker 2 has 0.598 grams, or sorry, moles of NaCl. My key says grams. I'm sorry, it should say moles, but I think the work is still right. Divided by the same 100 grams of solvent, so 0.0 kilograms. All right, and so then we get, the molality there. And so we should see that beaker 2 has a greater molality because there's more stuff dissolved. Okay, so we looked at an unsaturated solution and a saturated solution. Only one of them will accept more solid, the other won't. So let's look at these other questions. How does cooling the beakers change stuff? So how we know that NaCl will dissolve, that only 35 grams of NaCl dissolves in 100 grams of water is because when we look at a solubility table, right, it's usually solubility and time, temperature is our x-axis. If we read it, so if this temperature is like room temperature, we'll see that, at 20 degrees, only 35 grams of salt will actually go into solution. So our intuition says when we heat up solutions, more solid goes in. That's what our intuition says. That's why, when you're making Kool-Aid at home and you want to dissolve a bunch of sugar, sometimes you put hot water in first to dissolve all that sugar first, because you can just get more sugar into solution that way. So if we cool the beaker, typically solubility actually goes down. So if solubility goes down, will that 35 grams of salt remain in solution? No, because the solution won't allow it. Its solubility is changing. So what's going to happen? That solid has to fall out of solution, crystallize, and go to the bottom to maintain that solubility line. So cooling the beakers actually changes solubility. All right, changes solubility. But only one of them actually changes concentration. Only one of them will change concentration. It's the one that's already saturated, right? Because the saturated one has 35 grams dissolved. We cool it a little bit. Let's say we bring it to like 33 grams per 100 milliliters. You will lose that 2 grams. It'll go to the bottom. It'll go to the bottom. Versus if you cool beaker 1, it's already unsaturated. So as long as you don't cool it so much that you fall below that concentration, you won't see a concentration change. I think it's better explained actually in E. So let's actually talk about E. E says, okay, we heat a beaker. We heat the beakers. Our intuition says that solubility increases with temperature. All right, so if we take this picture, there's 35 grams of NaCl in the solution, 15 down here. If we heat it up to a certain point where now the new solubility is 40 grams of NaCl in 100 grams of water, what's going to happen? What's going to happen? Won't 5 grams in the bottom go into solution, right? So then the new concentration here is 40 grams, and how much is at the bottom? 10, yes, 10. But let's look at our unsaturated beaker. Let's see what happens with our unsaturated beaker. In our unsaturated beaker, we have 30 grams dissolved, but what's at the bottom? Nothing, right? So if I take this beaker and I increase the temperature and I change the solubility to the same, 40 grams per 100 grams of water, what's going to happen? Can this solution dissolve more? Will it dissolve more solid? There is nothing to dissolve, all right? So if there was solid at the bottom, it would dissolve more, but there's no solid there. So its concentration doesn't change. You literally just heated up the solution, that's it. Because there's no solid at the bottom, that concentration doesn't change. So In E, heating the beaker's solubility changes, and so beaker 2 will dissolve more solid. Dissolve more solid, and then the concentration you'll see goes up. But in beaker 1, you see no changes at all. That the concentration doesn't change, and the concentration just doesn't change. All right. What if we remove 5 milliliters of solution off the top of both beakers? How does that change things? Does it change the concentration of stuff? No, it doesn't. If we take 5 mils off the top here, all right, both of those will have the same concentration for both of them, all right? We're just like splitting it up. We're taking like a Gatorade and we're putting into 2 cups instead of 1 cup within there. And the detail here is we're removing it off the top. So in the saturated solution, we're not taking anything off the bottom. All right, but this is different for G. What if we add 5 milliliters of pure water? How does it change? How does this change? So in the saturated beaker, let's just think about it. You have solid at the bottom, you add more water, you're going to dissolve more solid. Because the idea is if we add 5 milliliters of water or 5 grams of water, instead of 100 grams there, of water, we now have 105 grams of water. So it can accept more solid. So in beaker 2, the saturated one, you'll see a decrease in the amount of solid at the bottom, but does the concentration of this saturated solution change? No, because we want to stay maintained on that solubility line. When we add more water, you're essentially going to dissolve more solid to fill that void, to fill that pure water until it gets back to its regular solubility, saturated concentration. Versus if you add water to the unsaturated solution, there's no more solid to dissolve. So it's just an M1V1 calculation. So it does become diluted, that the concentration does change. All right, evaporating. So a little bit different here. So it's kind of the opposite. If we evaporate 5 milliliters or 5 grams of solvent, now we only have 95 grams of water. So some solid's going to fall out of solution to maintain that concentration in beaker 2. But in beaker 1, the unsaturated one, the concentration does change because it's, again, just an M1V1 calculation there because we're unsaturated. Okay, so the question is here, so we didn't include the 15 grams of undissolved solid at the bottom in our calculation. That is correct, because when we calculate, we're calculating concentration of NaCl aqueous. That means it's dissolved in solution. So we're only taking into account what is actually in the solution, not the solid at the bottom. That's not included. Good point. Okay, so that's it. Okay, so yeah. Oh yeah, the evaporating one. Okay, so here, how about I ask it this way? Okay, so we have the, there's my saturated one, right? The saturated one. Oh, I'm in the corner. I don't want to be there. I don't want to be there. So the saturated picture right here, I have 100 grams of water, and you told me that you can fit 35 grams, dissolve 35 grams of solid. What if I asked you, what if you only had 50 grams of water? How much solid could you dissolve? Tell me. You have 50 grams of water. If I have 100 grams of water and I can dissolve 35, if I only have 50 grams of water, how much solid can I dissolve? Yeah, half of that. Do we understand that? Yeah? So it's the same thing here. We have less solvent to go around. So if I have 95 grams of water, will I be able to dissolve all 35 grams of that solid that's in there? No, some of it has to fall out to still maintain the 35 over 100 ratio. Does that make sense? Yes, okay. Yeah.
If a solution is like one of the beakers is at 35 grams of solute, is that saturated or unsaturated?
So the question is, if we had exactly 35 grams of NaCl and no solid at the bottom, is that saturated or not? The book says it is saturated because it no longer can accept solid, but me and the book disagree on that, and I'll just leave it at that. So if it's the book and if it's the exam, if you're on the line, it is a saturated solution because it can no longer accept solid. Yeah.
Is that still ultrafiltration? Like, is that area of the system that's still ultrafiltration?
Yeah. Yeah. So the question here is, how is evaporating 5 mils different from removing 5 mils? Because when we evaporate, we only evaporate the pure water. So we reduce how much can be dissolved, how much solid can be dissolved, versus if we just remove 5 mils off the top, we're not changing concentration at all, or the capacity for that solution to accept more solid or less solid. Okay. Questions from the gallery? What question do you want to do next? What? Okay, you want to do the next one? All right, Henry's law, yay. So Henry's law has to do with solubility of gases, like in my LaCroix. So I tell you the Henry's law constant for helium gas and water is 30 degrees Celsius, or at 30 degrees Celsius is this value. So it tells you the maximum amount of gas that can dissolve in solution at a given temperature and partial pressure of that gas above solution. So I tell you, all right, so there's the Henry's law constant for helium. What is the solubility of helium in water? That's in contact with 1 atm of pressure, but the mole fraction of helium is 0.25. So you have a total of 1.5 atm of pressure, but only a quarter of it is helium. So how we calculate partial pressure or solubility of gases using Henry's law, S meaning solubility. Typically, this is just given in molarity. The solubility of that gas that you would measure inside your solution is equal to the Henry's law constant. Is it a K? Yeah, okay. For that gas times the partial pressure above the solution of that gas. So, is the partial pressure of the gas 1.5 atm? No, that is, what did I say? It is the total pressure. So how do I get the partial pressure of this gas? So in this case, it's helium. We're doing helium. How do I get the partial pressure of helium? I have to factor in the mole fraction. So the partial pressure of helium is 1.5 atm times that 25%. All right, so the partial pressure of helium is something, I can't do math. It is 0.375 atm of helium. This is the number I put into the pressure equation, or the solubility equation. So the solubility of helium is equal to that constant 3.7 times 10 to the negative 4 molarity atm, and multiply by the partial pressure of helium. So 3.375 atm. Make sure your pressure units match. All right. So here's this example. What if I had a container, a closed container, all right, closed container, all right, and I had pure helium inside this flask and it had a partial pressure of 0.375 atm. What would be the concentration of helium inside that flask? If above the solution, pure, it was a pure sample of helium and the pressure, the total pressure was 0.75 atm. Would the solubility be any different? No, it wouldn't. So again, because the idea here, we calculated the partial pressure that helium exerts in this mixture. It's fine that it's a mixture, because the idea of what partial pressure is, it's the pressure what that component would exert if it was the only component there. If we had this system where it was just helium and it was the same atmosphere here, we would have the same exact solubility as well. All right. Okay. So, other questions. Actually, let's talk about solubility of gases. Let's think about the trends. All right, solubility of gases, it's different than solids, right? Our intuition says solids like NaCl, you can, the solubility in water increases with temperature, but with gases, how does it trend with temperature? As temperature goes up, solubility of gases goes down. Yes, because, or an example is, cold LaCroix is tastier than hot LaCroix, right? Like a nice cold soda. It like is so good, it like burns your mouth because of all of the dissolved CO2 in there, that at colder temperatures, that the solution can actually accept more gas particles. It can dissolve more of the gas, and it's tastier for us. What's the other trend? I think it's like as IMFs in the gas solute increase, solubility increases as well. So we see like heavier gases are typically more soluble. So CO2 is like a pretty heavy gas, has high LDF, so it has a pretty high solubility versus helium. Helium, again, only LDF, but it's really light, so it just escapes the solution altogether. So it's a very low Henry's law constant. All right, so I like to use the example, okay, we're gonna go to Starbucks and I have a hot coffee and I have a cold coffee, right? I have like a hot coffee and an iced coffee. Which coffee will accept the most sugar? Hot coffee, yes. Hot coffee, because with solid, sugar is a solid, and the trend is typically, most cases, solids increase their solubility with increasing temperature. Okay, which one could hold more carbonation? The hot coffee or the cold coffee? Cold coffee, yes. Nitro coffee is a thing. Yeah, nitro coffee. I've never had it. Is it good? You're nodding, so it is good? Okay. It's not good, but nitro coffee, right? It's not carbonated. What's the gas in nitro? Yeah, it's nitrogen. Yeah, it's nitrogen. Yes. I wonder, does it go flat faster? Why? It's what? Well, my LaCroix right here, it's the CO2 is going away. But let's look at, the question I asked is, does nitro coffee go flat fast? Let's look at the trends. N2 versus CO2 is lighter, so it's going to leave, yeah, so all that money you're paying for nitro coffee is just going into the atmosphere. All right, next. From the peanut up top, any requests? 25. Okay. The activation energy of this reaction is 95 kilojoules per mole. The rate constant at 25 degrees Celsius is this, that rate. Estimate the rate constant at 75 degrees Celsius. Great. So I always like to ask, what equation do we have to use? That's my favorite thing. The annoying one. Okay. So which one do we use? So if we look closely here, I have 3 equations that have activation energy. Which one do I use? 1, 2, or 3, which one? 3, yes, the third one. The reason we use the third one is because it compares the rate constants of at two different temperatures. We have a T1 and T2, we have a K1 and K2. So I'm giving you the information, at one temperature, I want you to estimate the new rate constant at this temperature. So the tricks here, all right, so ln K2 over K1 equals activation energy over R, T1 to the, how does the key do it? Is it K1 over K2? Okay, all right. So then this is T2 to the -1 minus T1 to the -1. So we just need to be real careful about where we put the values. So here are the common mistakes I always see. Activation energy is given in kilojoules per mole, but in the equation, it needs to be in the unit joules per mole. So 95 times 10 to the 3 joules per mole. The reason activation energy has to be in that unit is because the R that we use is which R? The joules per mole, so 8.314 joules per mole Kelvin. And so since we're using that R, joules need to match. We can't have a kilojoule on top, joule on bottom. That's no good. So that's probably the most common mistake. And now it's just being really careful of associating T1s and K1s together. So rate constant here is 0.15 molarity per second. So I'm going to call that K1. So that means 25 degrees Celsius is T1, but it needs to be in Kelvin. Do you know why it has to be in Kelvin? Is it because I told you so? No. Yeah, it's because of the R value. R has Kelvin in the denominator. Yeah. All right, so 298 Kelvin. Yeah. And then we are trying to figure out, okay, at this new temperature, 75 degrees Celsius, which is something, 348 Kelvin, all right? And we want to figure out what is K2, all right? And it's just plug and chug, but you need to be really careful about natural logs. All right, so putting in the numbers, it's natural log of K1, so 0.150 molarity per second over K2, that's what we're calculating. Activation energy, 95 times 10 to the 3 joules per mole. R is 8.314. T2 is 348 to the -1, and then 298 to the -1. All right, so it's just a bunch of math. All right, so I get the right side of the equation is equal to -5.509. And then I have natural log all this stuff. How do I get rid of the natural log? E where? Where do I E? Yeah, I have to E both sides. If I E both sides, then I free the fraction. All right, and then that natural log goes away. And so E to that one side is 0.00405, and we have 0.150 over K2. And so then we get K2 is like 37 molarity per second. So how can you check yourself? What is the trend with rate constants? Rate constants, as temperature increases, rate constant always increases, always. So does this number that we calculated make sense? Rate constant of 35 versus where did we start? 0.15. Yeah, so it increased because we increased the temperature by a lot. So yeah, there we go. Side question, what's the order of this reaction? Yes, it is 0th order. How did you get that? The unit. Yes, it is 0th order because of the unit. I always like to think with orders, remember that your rate law, your overall rate of your reaction is always in the unit molarity per second. Our rate law is K, our rate constant, times the concentration of your reactants. Right? So if you have a 0th order reaction, does your reaction depend on concentration of anything? No, that this value just becomes 1. So K has to be molarity per second. If it's 1st order, then you have to factor into that molarity that's there for the unit of K. So 1st order is the unit second to the -1 or time to the -1, it doesn't matter. Second order would be molarity to the -1, second to the -1. All right, so we don't actually have to tell you what the order is. We can just give you the unit and you should know. Okay. All right, next. 7. Okay, 7. Okay. All right. Concentration conversion. So I can guarantee you that there will be a concentration conversion on the exam. It's a learning objective. So I have strategies for these concentration conversions. We just need to be really cognizant of the units of everything. So I tell you, we have a density of this molarity of potassium chromate, and I ask you, what is the molality? So I always like to start with units. Molality, we already said this, is moles of solute over kilograms of solvent. So the tough thing with these questions is it's hard to know how to get started. So I always have a strategy. You need to start with some amount of solution, and I'm going to pick the easiest amount. Molarity, what does molarity mean? Moles per liter. So if I wrote this as an equality, there is 0.872 moles of my solute, so K2CrO4, in what? In what? 1 liter of solution. So I'm going to make this real easy for myself, and I'm going to pretend I'm starting with 1 liter of solution. You follow me? So if I start with 1 liter of solution, and we look at the mole, like this is our goal, right? We need to figure out how many moles of solute we have, how much kilograms of solvent we have. Do we have any piece of information already? If I assume we start with 1 liter of solution. Yes, we already have the moles of solute. We already have that. If we start with 1 liter of solution, that there is 0.872 moles of stuff. So we just need to figure out how many kilograms of solvent is present. That's the hard part. Okay, that's the hard part. But if I have 1 liter of solution, I can use the density to figure out how many grams is present. And I can figure out how much my solution actually weighs. So 1 liter is 1,000 milliliters. And then I use the density. So this solution is 1.129 grams per centimeter cubed, or milliliters. So that 1.129 is going to go where? On the top or the bottom? On the top. Yes, 1.129 grams, 1 milliliter on the bottom. So this will tell me how much my solution weighs, 1,129 grams of solution. What's the detail of the solution? Solution includes the mass of the solvent and the solute. So crap, I cannot put 1,129 grams. I can't put that on the bottom because I need kilograms of solvent. This is the mass of the solution. I need to figure out how much of this mass is the solute. How do I do that? I already know that I have 0.872 moles of solute present, so I just need to figure out how much that weighs, all right? So 0.872 moles of my K2 chromate stuff, molar mass, I even give it to you, 1 mole on the bottom, 194.19 grams. So that many moles of potassium chromate is something 169 grams of solute. Now can I figure out how many grams of solvent I have? Yes, you just subtract them. So the rest of the mass, right, you subtract that, we get that the mass of solvent, so in this case water, is equal to something like 959 whatever, or like 960 grams is your solvent. So in your denominator, you're going to put 0.960 kilograms. All right, and then there's your answer. All right, so we just need to be really cognizant of our units there. All right, so there's a lot of different molarity calculations possibilities, and so this is how I teach it. So in this one, so note how in question 7, I gave you the density and you had to use the density to answer this question. But what about this one? Let's calculate the mass percent of nitric acid that's this molality. I don't give you a density there. Did I not give you enough information? No, you can actually answer it without density. So this is how I kind of teach this idea. So the new concentration units we've talked about are mass percent, which is the same as like ppm and ppb. They just use different multipliers. We talked about molality. What else did we talk about? What else did we talk about? Mole fraction, yeah. And then I like to think, okay, we have molarity over here. Molarity over here is moles over liters of solution. I like to think these units, these concentration units, they live on an island together. As long as you know what the solute and the solvent are, you can interconvert between all of these. You don't need density. But if you want to go to the island where molarity lives, all right, in order to interconvert between these two, you need density. And the reason is because of the denominator in molarity. It's liters of solution. Mass percent is you're just working with gram amounts of solute and solvent. Molality is just kilograms of solvent. Mole fraction is moles of solute, moles of solvent. So molarity, because it's liters of solution, requires that density factor in there. Mole amounts, mass amounts, those are all additive, perfectly additive. Believe it or not, volumes are not always additive. Yeah. Yeah, so for mass percent, well, let's just do number 8. Okay, we'll just do number 8 and then I'll do it. So let's just do number 8. Let's calculate the mass percent of nitric acid in this molality solution. So I always like to start off with what is mass percent. Okay, it's your part over your whole. And so since we want mass percent of nitric acid, we need to figure out how many grams of nitric acid we have over grams of the entire solution. The solution includes what? The solute and the solvent. So really grams of solution is the grams of nitric acid present plus the grams of water that's present. So do understand that those are additive there. All right, and then to make it a percent, you multiply by 100. All right, so that's our goal. I need to figure out how many grams of water, or sorry, grams of nitric acid I have. I also need to figure out how many grams of water I have. And then I can calculate mass percent. So let's look at the piece of information given, 17 molality. And again, remind ourselves what the unit is. Molality is moles of solute over kilograms of solvent. So my strategy here is make it easy on you. 17 molality means 17 moles of HNO3 is in 1 kilogram of water. So I'm going to make it easy and pretend I have 1 kilogram of water. Because if I have 1 kilogram of water, how much nitric acid do I have? 17 moles. From 17 moles, can I figure out how much that weighs? Yes, you can. So that's my assumption here. I'm going to start with 1 kilogram of my solvent. So 17 moles of nitric acid, multiply by the molar mass. Oh, I even give it to you. I'm so nice. 1 mole is 63.01 grams. So you get that weighs something like 1,071 grams. That's of nitric acid. So that goes in my numerator. All right. So I have my numerator. Oh, and I have that part of the denominator. How do I get grams of water? What was the assumption I made? What did I start with? 1 kilogram of water. So grams of water is 1,000 grams. All right, and that's how you plug it in. It's all good. All right, and then multiply by 100, and that is mass percent. All right, so we'll actually do it here. So the mass percent will be 1,071 grams over 2,071 grams. All right, to get mass percent, so I'm going to answer your question now, the question about ppm and stuff. So this fraction, the part over the whole, to get to ppm and ppb, keep that fraction in your back pocket. To get to mass percent, you multiply by 100. That gives you the percentage. To get to ppm, you multiply 10 to the 6, so you multiply by 1,000,000. That same fraction, the same fraction we used, all right? We don't have to recalculate anything or anything. That will give you ppm, and then you multiply by 10 to the 9 to get ppb. And so the question is like, why would you ever want to use those units? Sometimes concentrations are really, really, really small. Scientists don't like to look at small numbers. We want fairly even, integer numbers to look at. So sometimes we'll put things in different concentration units so they look nicer to our eyes and to read. Okay. Yes. That's another way to do it as well, yeah. Is that in Fusa's key? Yeah, I'm not gonna touch that. So yeah, just ask him. Other questions? What? Okay. All right, do you guys, I did the questions on Zoom, but you guys are quiet. Is there a question you want to do? Or we're gonna just follow what Zoom wants, the Zoomers want. 22, what did you want to do? 9, is that the next one? Oh yeah, okay, we can just do 9. Okay, as moles of solute in an aqueous solution increases. So, we kind of did this already. We did this already. It's colligative properties. Oh, we have to go through all of them. So when we add more solute to a solution, we are making it more concentrated. So think about colligative properties. So mole fraction of your solvent increases or decreases when we add, let's say, salt. We're adding salt. Mole fraction does what? Of our solvent, sorry. It goes down. Yes, because it's no longer pure. Vapor pressure changes how? Of our pure from our pure water. It decreases. That's colligative properties. It decreases. Freezing point depression. What? Decreases because it's freezing point depression. More concentrated, lower freezing point. Boiling point temperature increases as we become more concentrated. So the last one here, osmotic pressure increases or decreases. Dang, this one doesn't have the answer in its name, but we can use the the equation. The equation for osmotic pressure is pi equals molarity, not molality, RT. So as solute concentration increases, M increases. So how does osmotic pressure change? Increases. Okay, so we'll just do 10. We'll just go in order. Here we have a solution of this compound, erythritol, okay? 2.5 grams of that in 5 grams of water, and it freezes at that temperature. What is the molecular weight of the substance, assuming it's a non-electrolyte? So if it's a non-electrolyte, this tells us something. It's Van 't Hoff factor. What is its Van 't Hoff factor? 1, yes, because it is not, there's no ions present. It doesn't break apart into ions in solution. It sticks together. It's a molecular compound. So this is freezing point depression. So we're going to use the freezing point temperature depression equation, TF equals I MKF. All right. So we're using that equation, but to the side here, our goal is to get molar mass of this compound. So what is the unit of molar mass? Grams per mole. So if I know the gram amount of this compound and I know the mole amount of this compound, I can figure out the molar mass. Do I have any of these pieces of information already? Yes, the gram amount, right? The question gives it to you. It's right there. You have 2.5 grams of it. So we already have that piece of information. We just need to figure out how many moles of this stuff are in solution. So we're good. This is where we use freezing point depression. So if this is the freezing point of the mixture, what value do we put into this equation? What value do we put in there? We put 0.773. That the freezing point was depressed by 0.773 degrees Celsius. All right. So we don't want, basically, when we're doing this calculation, we don't want the negative sign in there. That negative sign is going to screw us up. All right. We know what I is. We already said it's 1. We're going to calculate the molality because molality is going to help us get to our answer because it's moles over kilograms of solvent. Times Kf. Kf for water, I think it's 1.86 degrees Celsius molality. Is that what it is? Okay, cool. All right, but you're given that. I just pulled that out of my butt, but you're given that on the sheet. All right, and so we calculate for molality. So you get, in order to get this freezing point depression, your solution needs to have a concentration of 0.4156 molality. Is that my answer? Am I just going to put that value in my denominator? No, because that's the unit of molality. But what does the unit of molality mean? It means that there is 0.4156 moles of my solute in 1 kilogram of solvent. Do I have 1 kilogram of solvent? No. How much solvent do I have? 50 grams. So I'm going to use that 50 grams and the concentration here given to figure out, oh, how many moles do I have in that small amount of liquid? So 50 grams of my water, H2O. I'm going to put the 1 kilogram on the top here, but I'm going to just convert it into grams. So 1,000 grams is 0. Oh, no, that's wrong. No, I don't want to do that. Hold on. Wait, no. Okay, I'm messing up. Okay, so we're in the unit of grams of H2O. So sorry, the 1 kilogram of water needs to go in the bottom. So mass of solvent cancels, but I'm just going to be lazy and put 1,000 grams of water. So all I did was I just converted kilograms to grams here. And then for every 1,000 grams of water, there's 0.4156 moles of solute present. And so you get that in this solution, in this small little 50 milliliter sample, there is 0.02078 moles of your stuff present. That's also not your answer. Your answer, you need to shove that into the denominator. All right, so this question, 2 parts, right? Like we use the freezing point depression information to figure out the concentration required, and then we had to go back to the information given how much solvent in this specific experimental setup has a certain amount of moles. It's that value that goes into molar mass concentrations. Okay, all right, I'm done with chapter 13. Let's move on to chapter 14. So does someone have a question 20? Perfect. All right. So 20. Okay, actually before we get to that, I want to talk about kinetics and rate laws. So we've talked about rate laws, right, where we have like rate equals K, our rate constant, times concentrations of, reactants and stuff, like M and then N, okay? So that's our rate law. We talked about 3 different ways to calculate rate law. 3 distinct different ways. The first way we calculate rate laws is the method of initial rates, where you're given a table, you see concentrations of your reactants change in different experiments, and you look at the initial rates. These are the table questions. Where's my key? Where's one that's like that? So number 22. Number 22 is method 1, you use initial rates to figure out what the order is. So like, for example, if you double the concentration of your reactant and your rate doubles as well, that tells you that's a first order reaction. If you triple the concentration of your reactant and you don't see any change in initial reaction rate, what's the order of your reaction for that reactant? If you triple the concentration of your reactant and you see no change in reaction rate, does your reaction depend on the concentration of that reactant? No, so what's the reaction order for that reactant? 0, yes. So that's the method of initial rates. So the second way that we've built rate laws is, what's the next one? Graphing. Graphing, where you might graph a reactant over time and you see, oh, the concentration, decreases, but it's like a weird shape, right? And so with graphing, you're typically graphing, concentration with time. And so what we see is if you change your y-axis, if you manipulate the data in a way to make a straight line, because right now, is this data a straight line? No. This graph, what is this graphing right now? The axes. What kind of order reaction is this graphing? A 0th order, because I didn't make any changes to concentration here. So this tells me that this reaction is not 0th order, because it's not a straight line. We always are looking for straight lines. So if you regraph it with a natural log instead and you get a straight line, that would mean that that reactant is first order, right? But let's say you did it and it wasn't a straight line. What would be the next plan of attack? Graph it as a second order. What's the y-axis on a second order graph? Yeah, 1 over. So you just manipulate the data, make it 1 over, and then hopefully you pray that it is a straight line, right? Or whatever. I don't know what direction it should be. I forget, right? And so in this case, straight line, second order, it's a second order reaction. All right, so that is the second way. And then the third way, which I feel like at least is my class's favorite, is mechanisms. Mechanisms, where I yelled at my students the very first day and I said, you cannot assume that the coefficients is the reaction order for steps, for methods 1 and 2. I can't just look at this reaction and be like, yep, that's a second order in terms of, with respect to N2O5. You cannot do that for these two reactions, for these two methods, initial rates and graphing. But you can. In mechanisms, when you're inspecting elementary reactions, you can just turn coefficients into orders, only for mechanisms, only when the reaction is elementary. In this reaction, it's not necessarily elementary. We actually have to use experimental data to get the reaction orders, meaning using methods 1 or 2. But it's only for mechanisms that are comprised of elementary steps where we can just take coefficients and turn it into orders. So that's the big thing. There's the 3 different steps, 3 different ways. Do recognize they're different. So what number are we doing? 20? So this one is a mechanism because I give you steps. So this is method number 3. I give you steps, 2 steps, a fast step and a slow step, and I want you to tell me what is the correct mechanism. So the trick is with mechanisms is that the slow step always determines the rate law. Say it with me. The slow step always determines the rate law. So in this reaction, which step determines the rate law, the first one or the second one? The second one. So if this is an elementary reaction, all we got to do is say rate equals K2, I'm just going to call it K2, times concentration of NO3 times concentration of NO. Bam, my hands are clean, I'm done. But am I done? What's the problem? There's an intermediate in this, in my rate law. Are we allowed to put intermediates in our rate law? What are the only things that can go in the rate law? Reactants, right? So all of the reactants that I'm allowed to have in the rate law can only either be NO or O2. NO3 is not something I can take from the shelf and add to this reaction. So I need to get rid of that intermediate. NO is fine. It's the NO3 that's screwing things up. So the strategy here is you take now the fast step, and you take the fast step, you assume it's an equilibrium where the forward rate is equal to the reverse rate of the reaction, right? So the rate law of the forward direction is equal to the rate law of the reverse reaction. And so we write the rate law for the forward and set it equal to the rate of the reverse. That sounds confusing, but it's not that bad. Where we take the reactants, so K1 times NO times O2 equals the rate law for the reverse reaction. So it's K -1 times what? So what's that's the product now. The product is the reactant in the reverse reaction. So it's NO3. All right? So how does this help us? We can now build an expression that helps us get rid of NO3 and just have reactants. So you just rearrange those things. You get that NO3 concentration equals K1 over K -1 NO times O2. And then you just plug all of that into the rate law to get rid of the intermediate. Did I mess up? No, that's right. That's right. So if you rewrite it, I'm just going to rewrite all the K's as just one K, K overall. All right, we don't need all the little K's here. So what we see here when we plug in this expression in for that intermediate we're trying to get rid of, we have NO squared and O2. All right, and so that's the answer. So A, I think it's A. Yeah, it's A. Good. I like rate laws. So let's pretend, let's go back to this reaction and say, or this mechanism, what if I said that the first step was the slow step and that was the fast step? What would the rate law be? What would be the rate law? Yeah, it'd just be NO times O2. That's it. And so the rate law would be B if the first step was the slow step. That's it. The slow step always determines the rate law. Okay, let's answer 21. How would we draw an energy profile diagram for this mechanism? Oof. So the original one, where the slow step's the second step. So it's not that bad. This reaction happens in how many steps? It happens in 2 steps. So how many activation energies do I need? 2. Yeah, that's it. So I need to draw a graph. Okay, that has 2 humps on it. So one, but the detail is here is that the second step is the slow step. So what's going to be special about the second step? Its activation is going to be what? Big or small? Big. It's going to be really big because it's slow to get up a big hill. So I'm going to like really exaggerate it. All right, so something like that. All right, so where in this graph will the concentration of NO3 be the greatest? In the little well, yeah, because that's where intermediates live. They only exist for a small amount of time before they're used up to make products. Okay. So, great. Okay, so fine, we'll do 22 as well. We'll just do one of each. So, because remember, 3 different ways we got reaction rates, or rate laws. We just did mechanisms. The slow step determines the rate law. Now we'll do initial rates. All right. So I tell you, okay, this data was collected for the disappearance of NO in this reaction. What's the rate law? So the strategy for this question is we want to see, okay, changing the concentration of reactants, how does that change the overall initial rate? All right, so the strategy we want to use is look for experiments where the concentration of one reactant changes, but the other one stays the same. So I'm just going to look at these first two reactions. So these first two reactions, O2 is staying the same concentration. So I know any change in reaction rate is not a result of O2's contribution. Any change in reaction rate is only coming from NO because that's the only substance that's changing. So here's how I, think my way through this is, okay, going from experiment 1 to 2, how is NO concentration changing? It is doubling. Cool. O2 staying the same, so we can ignore that. Initial rate, how does that initial rate change? It increases by what fold? 4. So if NO doubles, but we get a 4-fold increase in our initial rate, what does the order of NO have to be? 2, because 2 squared equals 4. That's why. So NO is second order. All right, cool. So we have NO now. We just need to figure out oxygen. So I'm going to look at different experiments here. I'm going to look at experiments where NO stays the same, but I don't necessarily have to because now I know the order of NO. Any change in NO can now be accounted for, but it's just easier if we look at experiments where the other reactant stays the same. So NO is staying the same. How does oxygen change between reactions 2 and 3? It doubles. How does the reaction rate change? Do note of the scientific notation here. So this is like 0.113 and this is 0.0564. So the reaction rate is changing how? It's doubling. So what's the order of oxygen? It's 1. All right, so that gives us our basic rate law. We still have K to worry about. All right, so there's our rate law. But part B is asking us, okay, now calculate the rate constant. How do we do that? We just use any experiment and we plug in the information. Plug in the data, solve for K, that's it. So which reaction do you want to use, or experiment, 1, 2, or 3? The first one, y'all so boring. 3? Okay, let's do the third one. But just prove it to yourself, all right? You can use any experiment. You should always calculate the same K for all of them, all right? But we'll do reaction 3. So the overall rate is 0.113 molarity per second equals K, that's what we're solving for, NO concentration 0.0252 molarity squared times 0.0250, whatever, and then just solve for K. And then so the unit here is tough. So I like to think, okay, there's a total of molarity cubed on this side, so the unit of K has to be molarity to the -2, second to the -1 in order for all the units to work out. So the rate is molarity per second on the other side. So we just got to be clever with units. You don't have to memorize, what's a 0 order, first, second order unit. You might already just know it because you've seen it so much, but you can think your way out of it too by just using units. And so there's some answer, just do the math. All right. Oh, and then here for C, how would you do C? Calculate the initial rate of consumption. Okay, let's just do it. Dang it. What number is this? All right, so K is 7.1 times 10 to the 3. Great. All right. So here, this question is saying calculate the initial rate of consumption of O2 when the concentration of these things are that. So in this example, we would just be putting new concentrations into our rate law and calculating rate because now we know K. Now we know K, all right? And so you just plug in those numbers and get a new rate. And then this question, so if you plug in those numbers, you get that the rate that I have defined as the consumption of O2. All right, in molarity per second, we calculate it, it's 0.400 molarity per second. All right, that's of oxygen consumed. Now this question says calculate the initial rate of production of NO2 at those same conditions. So I already know that O2 is consumed at this rate. If we looked at the balance reaction, for every 1 O2 that we consume, how many NO2s do we get out? 2. So the rate of NO produced is going to be double the rate of O2 consumed. And you can think a bit about it like stoichiometry. 1 mole of O2 is 2 moles of NO2. And so we get that the rate of production of NO2 is 0.800 molarity per second of NO2. And so the detail here, and this is oftentimes confused, you know, I tell my students, like, you can't use coefficients to write your orders of your rate law. What the coefficients do mean are comparing the relative rates of consumption and production at any certain time in your reaction. So in this example, you know, O2 is consumed, NO2 is produced twice as fast. NO is also consumed, but twice as fast as O2. So stoichiometry relates the rates. Stoichiometry does not tell us the rate law. It just tells us the relating the different rates at a certain point in time. All right. Okay. Other questions? 24. Okay. All right. We have this this reaction. We plot 1 over BRO minus versus time, and it's linear with that slope. If the initial concentration of BRO minus is 0.80 molarity, how long will it take 1 half-life of BRO minus ion to react? Okay, there's a lot going on here. So, how I've graphed it, this tells us something about this reaction. What does it tell us? It's a second order reaction. Great. Why do they bother telling me the slope? The slope is the rate constant K. Yes, it is equal to K for a second order reaction. And note, yes, it's the right unit. So they tell me the initial concentration of this reaction, all right, BRO minus, the initial is 0.80 molarity. How long will it take half of that Br minus ion to react? So a half-life. We want to figure out how long does it take for that BRO minus to reduce to what concentration when thinking about half-life. Half-life means that we reduce the original concentration by half. So the concentration we're looking for here is what? 0.4, yes, 0.40 molarity. So there's a lot going on here. So I actually want to go to the equation thing. There's actually a couple ways we can do this question. All right. So we're using one of these equations given in here. So notice we have different half-life equations. They're different ones because there's different equations for different orders. So we see 0th order, these two, these are first order, these are second order. No, they're not. Yes, they are. Wait. Yes, okay, good. So we want to use these ones, right? Okay. We can actually do this question 2 ways. two ways. So I'm just gonna copy these, all right? And you can pick which way you wanna do. So one way, we're trying to calculate half-life. That's what the question is saying. We know the initial concentration of my reactant, BrO minus, it's 0.8. We know K, our rate constant, that's given right here. So we can just plug and chug and calculate the half-life. So let's do that. 1 over K, 0.056, molarity to the -1, second to the -1, times the original concentration, 0.80 molarity. And so you see these molarity units cancel, and we have a negative, an inverse second in the denominator. So T1/2 is going to have the unit of a second. And so you get 0.0596 times 0.8 to the -1, nope, 0.0 to the -1. You get 22.3 seconds. That's all right? Okay, good. Great. So you can use the T1/2 equation, but I personally don't like the T1/2 equation because it only works for one condition. It only works when you are having your concentration, turning it from 0.8 to 0.4. That's the only time it'll work. Or if you're starting with 1 molarity, going to half a molarity. What always works every single time is the integrated rate law for the second order reaction. So this first equation, it always works as well. We just need to make sure we put in the right values. So 1 over this isn't initial concentration, 1 over concentration of your reactant at some time. That is this first species, 1 over concentration of A versus 1 over concentration subscript 0 means initial. So you're taking the inverse initial on this side while you have the inverse concentration you're looking for at a certain time on the left side here. So putting this equation together, we're going to do 1 over 0.40 molarity equals K, which is given 0.056 molarity to the -1, second to the -1, T, that's what we're solving for, plus 1 over 0.80 molarity. So try it both ways. Solve for T. Do you get the same number? You're just going to trust me that you get the same number? You will get the same number. You'll get the exact same number. I like this equation better because, again, this T1/2 equation only works if you're having the concentration of your thing. What if I asked you, what if instead of, I asked how long will it take one half-life for half of the thing to react? What if I said, how long will it take for the new BrO concentration to be like 0.1 molarity? Can you use the T1/2 equation? Nah, no, not really. We would have to use the integrated rate law instead. But no problem, we can just insert that concentration into the bottom here. That's it. And then we just get a new time. That's it. Okay. All right, what's next? All right, so we did 25. There's 25 minutes. I don't want to do that one. Yeah. Oh yeah, like this question. Okay, perfect. The decomposition of N2O5 follows first order kinetics. Okay, is this the right question? Yeah, okay. Suppose we start with an unknown amount of N2O5, but after 11 minutes, after the start of the reaction, 30% of the N2O5 disappears. What is the half-life of this reaction in minutes? I love it. This question's a lot better than the other one, I think. Because we actually have to use both equations now. So the details here, it tells us first order kinetics. So if we go to the helpful hints, supplemental information, we want to use these equations. All right, the natural log ones, all right? So we just need to be real careful about concentrations of stuff and what variables we assign them in. It sounds like we are trying to calculate how much stuff we start with. So N2O5 initial, I'm just going to call it A, actually. I'm just going to call it A of our reactant. Initial, we don't know what that is. But they tell us after 11 minutes, the concentration is what? If 30% of the N2O5 disappears, how much is left after 11 minutes? 70%, yeah, 70. So I'll just say 70. You can put 0.7, it doesn't matter, all right? Oh no, that's not what we're solving for. Okay, so if 70%'s left, how much did we start with? 100%, very good, okay. Now this question's going a different direction. That's what I get for not looking at the key, right? So we started with 100%, we lost 30%, so we have 70% left. That's at some time. Do we know how long it took to get there? 11 minutes, so T is 11 minutes. This is the common mistake students will do, okay? They see, oh, it's asking for half-life. I'm gonna shove 11 minutes into the T1 half equation. But T1 half means the time it takes to lose half. You can't do that. The process for this question, using all of this information, we can actually insert it into the first integrated rate law, okay, not the T1 half equation. If we insert all of this information into the first equation, what variable can we solve for? K. Once we have K, then we can shove it into the T1 half equation. Yeah? Okay, so let's do that. So natural log of what? I'm gonna take natural log of what number? 70. Yes. Prove to yourself, you can put 70 or 0.7, it's not gonna make any difference. Equals natural log of 100 minus K, that's what we're solving for, T. So 11 minutes. So K is gonna have the unit of what? Minutes to the -1, minutes, all right? So K, when you solve for this, equals, I don't know. I don't know, it is 0.0324 minutes to the -1, not seconds. I know we worked a lot with seconds, but this is in minutes because it needs to match the time we put in. All right. Okay, that's not our answer. We need to shove that into the T1 half equation. T1 half will be in what unit? Minutes. So this T1 half equation for first order, it's natural log of 2. Natural log of 2, that's equal to 0.693 over K, so 0.0324, and you get that it is, it takes 21.4 minutes for you to lose half your sample. Does that answer make sense? It takes 11 minutes to lose 30. It takes 21 minutes to lose 50? Yeah. If you got a number, if you went through this and you got T1 half equals 5 minutes, does that make sense? No, it don't. It means that it took less time to lose half of it? No. So think about the answers you're reporting that can save you some time. Okay. All right, so I like 17 better than the other one. The other one that we did with the BRO minus, I like this one better because I force you to use both of the reactions. I know a lot of students, they try so hard to shove that 11 minutes into the T1 half equation because they see a T, right? They see T, they feel comfortable and safe with T, but you can't do it. You gotta use the integrated rate law. Which really, the T1 half equations are the integrated rate law where we set like initial concentration and concentration at some time equal to a half. And so it's the integrated rate law just with a mask on. All right, so we want to do 16. All right, so given this, given this rate law, what is the initial rate of the reaction when the initial concentration of A is this concentration? Cool. So they give us K. So remember what the rate law is. Rate equals K times concentration of stuff to some order. But I don't know the order, or do I? Do I know the order? Yeah, the order is implied in the unit of K. So given the unit of K, what is the order? It is 1. Right? Don't think that we didn't give you enough information. I make sure we give you enough information, but just the bare minimum. I always make sure that just the bare minimum is given so you can answer a question. So that's the idea. Like students might see this and be like, I can't answer it. I don't know the rate law, but you do from the unit. So I tell you that the initial rate of the I'm asking, and I tell you the initial concentration is that. So literally all you do is multiply those two numbers together, right? But given the unit, maybe you know, it was a unit for a second order, you might have to square that A concentration, all right, given the unit of K. Okay. How can you tell the order based on the unit? It's because rate is molarity per second. Based upon the order, you'll have a different exponent in molarity, and you just need to figure out what K needs to be in order to have the unit of molarity per second. It's just a unit thing. I mean, you can memorize it, just that 0th order is molarity per second, 1st order is just per second. What's it next? 2nd order is what? -1, -1. 3rd order would be -2, -1. So I don't know. I don't know how you want to do it, but I do it from units. Okay. Okay, I guess we'll just go in reverse. Oh yeah, this one. Okay. The reaction that occurs in a breathalyzer is given. There is the rate of appearance for the chromium sulfate is 1.24 moles per minute. So that's of Cr2SO4, 3 of them. And I ask at that particular moment, what is the disappearance of ethanol? So I talked about 3 different ways we get rate laws. Students mix up this question. This question isn't a rate law. I'm just asking you, if this reactant is consumed at this rate, what is the consumption or production of another reactant? All we need to do is use stoichiometry. So if we look at the stoichiometry here, for every 2 chromium sulfates that are produced, how many ethanols are consumed? 3. So all we have to do is freaking stoichiometry. 2 over 3, and then that's the rate of consumption of ethanol. That's it. And so the answer, I think, is, I don't know, C? I think it's C? Yeah, that's it. I like to relate it to like cheese and bread. So 2 breads plus 1 cheese equals 1 sandwich. So if I consume bread at 2 breads per minute, how many cheeses do I consume at that second as well? 5 cheeses per second. How many sandwiches do I produce at that moment in time as well? 5. And again, it's just relating stoichiometry. There's nothing, so yes, we can use the coefficients, but this isn't the rate law. We're just comparing absolute rates, measured rates at different times. And it's dictated by stoichiometry. Okay, anything else? If not, I kind of want to be done. Last questions? Any last questions? We want to be done. We're going to be done. Okay, all right. I'm very tired. Okay. Thanks, guys.